giving me this chance to give a talk here, because initially I intended just to give a poster, and they offered me a talk, and I was very surprised. And actually, this is my first time to give a public talk, so I'm kind of nervous. Hope it goes smoothly. And secondly, I'd like to thank everyone who's still sitting here, because kind of the last talk, and you are kind of starving. Okay, so my name is Wang. I'm from Penn State. I'm a PhD student under the supervision of Dr. Long-Sung Chen. And the topic of my talk is deterministic domain switching in ferroelectric thin films by mechanical probe, and with a focus on the effect of flexoelectricity and piezoelectricity. And majorly, I'm doing the simulation work of this project, and our collaborator, Dr. Noe from South Korea, their group is doing this experimental part. Okay, let's get started by a brief introduction of the flexoelectric effect. And the flexoelectric effect is defined as the coupling, an electromechanical coupling between the string gradient and the polarization, which is like a kind of extension of the piezoelectric effect. And we can also understand this effect by thinking of the string gradient create a driving force for polarization. And people call this flexoelectric field, or in short, just call it flexo field, because it has the same unit of the electric field as the driving force for polarization. And the idea I want to emphasize here is that the flexoelectric effect scales with size. As we can see, there's a gradient term here. So as the system size goes down, this flexo field could be very large. Here's several examples. So from a microscopic perspective, people use a laminar single crystal to bend it with a probe, and to use this geometry to measure the flexoelectric coefficient. I use F here. And in this case, we can estimate the flexo field to be of the several voltage per meter to this magnitude. And this is used for measuring the constants. And if we go to a smaller scale, like this unimorph structure, we can use this bending mode to make energy harvester and actuator sensors, like shown in this example work. And we can see that because the system size goes down, this flexo field increases several magnitudes. And as we go smaller and smaller, for example, like these heteroepitaxial films, because the string will relax as the film thickness grows, so there will be a built-in string gradient in the film, which will lead to, as reported, the imprint effect and also the dielectric constant degradation in the materials. And the most significant case where the flexoelectric plays a role could be the pressing of a scanning probe tip onto the film sample. And it has been shown that this high flexo field could create polarization switching, 180-degree polarization switching, and also it will influence the effect transport locally in the systems. So my interest is focused on this scheme where the flexoelectric effect plays the most significant role. So the mechanical switching, it has long been known that the mechanical stress can influence the polarization. For example, in this work, we can see they use a local probe to reversibly control an A domain within the C domain in a PZT material, thin films. And the interest in mechanical switching majorly arises from this work in 2012 by Dr. Blumerman's group from Nebraska-Lincoln University. They found the mechanical tip could write 180-degree domains in the ultra-thin barium titanate films. And they define a critical force, which is, we can draw an analogy to the coercive field for the electric-induced switching, which is the threshold force to create this mechanical switching. And after that, several groups have found a similar phenomenon in different cases, like this work is the mechanical switching in PZT films. And also they found that by tuning the misfit string of the substrate, we can tune the critical force. And this mechanical writing phenomenon is also observed in the ferroelectric polymers. Here they just use very small force to write arbitrarily any pattern as they like. And this mechanical switching has also been used to switch both the ferroelectric and the ferroelastic domains, like this case in given ferrite. And also last year, also by Dr. Blumer's group, they put a graphene electrode onto the sample to make a graphene electrode-based capacitor. Still, using mechanical tip, we can penetrate the graphene top electrode to write any domains as they want. So from these several works, we can find several observations. First, the mechanical induced polarization is general in ferroelectrics, no matter in the common perovskites or in the polymers. And also it offers a voltage-free method to reverse the polarization, which can help us to avoid some problem from electric switching, like charge injection or the leakage problem. And also the critical force for achieve this switching depends on the misfit string, heat radius, and film thickness, and other factors. And also in all these cases, both the ferroelastic and the ferroelectric switching is involved. And also this is related to the piezoelectric and flexoelectric effects at the same time. And from a theoretical perspective, this phenomenon has been studied from our group by phase field modeling. And a simple picture of this we can understand like that. So when there's a homogeneous local stress, it will only reduce the barrier for switching, only reduce the magnitude of the barrier, but not change the shape of the free energy profile. But when there's a string gradient, because of the drawing force creates so-called flexo field, this will break the symmetry of the energy profile and make one state more favorable than the other one, which leads to the mechanical induced ferroelectric switching. And this flexo field is calculated to be very high, which could be to the magnitude of 10 to the 7th, and this is comparable to the coercive field for electric switching. And both the out-of-plane flexo field and the in-plane flexo field, they could have the same magnitude. And one another observation from Dr. Blumer's group recently is that when the tip is moving and when the tip is immobile, the flexo field created under the tip are different. So the message is here that the in-plane field could be comparable to the out-of-plane field, and the probe motion could influence the distribution and magnitude of this flexo field. So this makes us to think of that. First, for all previous cases, people only focus on the out-of-plane flexo taking into account the in-plane flexo field, which could also be significant. And we make this hypothesis that the lateral motion of the probe could be used to tune the in-plane flexo field, by which we could realize deterministic polarization switching. We choose the model case in Bizen ferrite because there's both ferroelectric and ferroelastic domains exist. And also both the piezoelectric and flexoelectric effects could play a role in these cases. And another thing, because as we know, the Bizen ferrite is a multiferroid, and people need to use to deterministically control the polarization switching path to realize electric field-driven magnetization switch. So if we're doing this, we first make an estimation of the flexoelectric field in BFO. Because there's actually no report of the magnitude of the flexoelectric coefficient for this BFO case. So here we just use the coefficient for barren titanate as a crude estimation. We can find that when there's no friction, the in-plane flexo field could be even larger than out of plane in this case, in BFO case. And after we consider the frictional force along different directions, the in-plane, the out-of-plane flexo field remain like similar shape, and the magnitude doesn't change too much. But the in-plane field significantly change the magnitude, and also the shape of the in-plane field change very much. For this case, when the tip is moving to the right side, the left-hand side is enriched. But to the opposite way, the right side has been enlarged. So we can find that the in-plane field could be comparable or even higher than out-of-plane flexo field. And also the friction breaks the symmetry of the flex field, and it also significantly enhances the magnitude. And this makes us to think of this scenario, that for a monodomain BFO, let's say it has a R1 state, the polarization directs to 111. And when the tip is pressing onto the film, because of the flexo field, it will induce either 71 degree switching if it slides to the direction of, this should be -1, -10. Or when it slides to the opposite 110 direction, it could induce 180 degree switching. So then we tested our scenario by experiments. And so our collaborator grew a 100 nanometer BFO on this miscutted substrate. So this miscutted substrate makes it the S-grown state to be a monodomain state, as can be defined from this RSM figure, and they also characterized it by PFM, both the in-plane and the out-of-plane PFM, and confirms the monodomain state. And this monodomain state can also be probed by the scanning probe. And then the use a rotary motion of this tip, like this square, to just apply a mechanical force of around 5 micronewton, but no electric involved. And they found that the out-of-plane contrast is observed in all of the edges of this path. But for in-plane PFM, only these 3 lines where the tip is moving to the right side has the contrast. And when the tip moving to the left, there's no contrast of the in-plane PFM image. And for the perpendicular directions, there's a mix of the contrast. So this means that when we sliding to the right-hand side, there's a 180-degree switch because of both change of contrast in out-of-line input. While when we get into the left side, which is the -1, -1, there's a 71-degree switch, like this. And we try to understand this by our phase field modeling. So one advantage of phase field model is that we can arbitrarily switch on or switch off the effects. So let me first give a brief introduction of the phase field model. Since Dr. Yes, I'll just give an introduction. I'll be very quick in this slide. So majorly we have a total free energy term, which is from the Landau phase transition theory. And for this case, because we consider the Flexoelectric effect, there is also a term in their free energy. And this Flexo term contributes, for one thing, is contributes the stress-free strain, like the spontaneous strain of the system, and also it creates a joint force as a Flexo field. And then the polarization dynamics is described by the time-dependent Landau-Ginzburg equation. And at each time step, we assume the elastostatic equilibrium, which is to solve this mechanical static equation with the boundary condition given by, for the surface, we assume a Hertz contact model with spherical tip. And at the same time, the electrostatic equilibrium is also solved with short circuit boundary conditions. And here's some parameters for the simulations. All the parameters are from our previous work. So first we study when there's no effect, a flexoelectric effect considered in the case what will happen. So the tip, as you can see, if there's no friction force, just press the tip onto the film for only the normal force. It will create 71-degree switching. The polarization from R1 is changed. R1 plus is changed to R3 minus. And when we consider the frictional force, it will either enhance the 71-degree switching if we switch to the minus 1, right? Minus 1 O direction, or to the opposite side, it will slightly inhibit this 71-degree switching. This is observed after we unlock the key. So in this case, the 71 domain remains stable while that one will disappear. And so we can draw the conclusion that the electric effect itself is enough to create this very elastic 71-degree switching. And the frictional force, it may either enhance or inhibit 71-degree switching depending on the direction of the frictional force. And then we add into the system the flexoelectric effect. And when it is considered because of the flexo field, it will significantly change the direction of the polarization under the tip. And after we consider the frictional force, it will either achieve this is 180-degree switching, and to the left side is a 71-degree switching. And after the tip is removed, we can find a stable 180-degree domain, and in this case, the 71-degree domains. And we can see that the flexoelectric effect is responsible for the observed 180-degree switching in experiments when the frictional force is to the right side. And also, the flexoelectric effect enhances 71-degree switching because this switch region is larger than the previous case without flexoelectric. And from the experimental case, they also consider the 2D scanning, which means to use a tip with a fast scanning axis, length and force, and at the same time moving to the another direction perpendicular to the fast scan axis, which is a slow scan axis. And as expected, this will either create 71 degrees switching here when tip moves to the -1, -10, while it achieves 180 degrees switching when tip is moving to the 110 direction. And for the intermediate case, which means these switching directions rotate 45 degree and 90 degree and 175 degree, they can find a mixture of the 71 degree switching and the 180 degree switching in these cases between them. So it's like for the left side, only 71 degree switching, and for the middle cases, it's a mixture, and for the right side, slightly, it's 180 degree switching. And our physical model also captures these features that we can see in all these cases. The out-of-plane polarization changed from upward to downward, but the in-plane cases, this one is enhanced, while this one is switched, and for the other case, it's like a medium state. And we can see here that only the 71 and 180 degree switching are observed, and the fraction of each switching depends on the tip motion. And also, the switching path only depends on the slow scanning directions instead of the fast scanning directions. And we further compare our mechanical writing of the domains with the conventional electric writing. And also, for the 1D scan, to use this one is for the mechanical switching case. I use the same figure from previous slides, and this is electrical switching. You can see that for electrical switching, both the out-of-plane and in-plane contrast has been changed, no matter which direction the tip is scanning. And for the 2D scanning, also we compare the mechanical and the electrical. We found that also in the electrical case, only 180 degree switching is observed, but mechanical, you can choose between the 71 and the 180 degree switch, depending on the tip motion. And we give a possible explanation that is because when the out-of-plane flexo field has the same magnitude of the out-of-plane electric field, the in-plane flexo field will be significantly larger than the in-plane electric field. So that's why in mechanical case you can observe a 71 degree switching, while in electric case the in-plane field is not large enough to achieve that. And so this is the possible explanation of us. And here comes the summary of this work. So first we achieved the deterministic polarization switching by virtue of modulating the lateral motion of the scanning probe. And also we attributed this phenomenon both to the piezoelectric effect and the flexoelectric effect, and they play like a synergy role in these cases. And finally, only the mechanical writing offer an static domain switching, while the electric writing cannot achieve this. So that's the take-home image I want to share with you. So finally, let me thank my collaborators and State University and the collaborators from South Korea, the Seoul National University. Thank you everyone.
I have a a general question. Experimentally,
Yes.
if you have a freestanding film, maybe you can do this flexoelectricity experiment more easily. Anybody has done? And also, if you do have a, let's say, nano tube, nano rod,
Okay.
you can bend all these things easily.
Okay.
So anybody has seen this flexoelectricity in nano tube by bending?
To my knowledge, no.
How about freestanding film? 2D and the freestanding?
So film, you mean there are no substrate,
No
just a
substrate.
film.
Yeah.
How big is the film?
Well, I don't know. I mean,
You mean very thin film, not the bulk crystal.
Like these ones like Harold Wang's been doing,
yeah,
right?
for example.
Okay, I think there's a theoretical prediction of the thin film bending and how much the flexo response they will get, but not experimentally.
Debbie?
In your modeling,
Yes.
how many different coefficients, or how did you model the flexoelectric tensor, which I guess for a cubic material has 3
Yeah.
independent,
Yeah.
and if you go to lower symmetry than cubic, it gets bad very fast. So what did you do about that?
Because this film modeling with the reference state is a cubic phase, so
Yeah.
we only need 3 independent parameters. And since there's no report there, I actually, it's the trickiest part. I did like a parametric study of all these 3 independent coefficients with, I just consider either it's positive or negative, and to see which part plays a real role. And what I found is that only when these 2 are positive and the shear components are negative, they are related to what we observe. So, yeah, majorly they should be positive.
I would say you're using experimental observation to back calculate the coefficients.
Actually, it's really hard to measure these coefficients in this experiment. Because, especially for Gibbon ferrite, you have to measure it.
You just mentioned that the sign is actually important, right?
The sign, yeah.
Yeah.
I mean, experimentally we observe. So for this case, it should be 180-degree switching, but if it's the negative, there's no 180-degree switching. So
That's my point. It seems that you're using experimental observation
yeah,
to back calculate the coupling coefficient.
Yeah, so this is a great way to go and figure out what the coupling coefficient is.
yeah, because it's still controversial whether this coefficient should be positive or negative in the flexoelectric related studies. People have been arguing for decades.
Yeah, actually, my question is really as a follow-up of Shi's question. So I'm thinking if due to the uncertainty of flexoelectric coefficient, if you change the signs, actually there's still some debate on the signs of flexoelectricity, not only magnetism.